Okay, so I want to do this one. Use perturbation described in the notes with the strategy outlined to prove the weak maximum principle for harmonic functions. Part of this is that you have to state the weak maximum principle. Okay, so I'm going to reason through this. I'm going to first give, after I state what the weak maximum principle is, I'm going to first give a wrong solution or a solution that's not going to work, but I want to explain to you why it doesn't work, and that will show you why we have to use this perturbation method. Okay, so first, the weak maximum principle. So the weak maximum principle says the following: let omega be an open, bounded domain. Now, we could say it's an open set with compact closure would be another way to say that. But omega be an open, bounded domain, and we're just going to assume here with smooth boundary, okay. Or with piecewise smooth boundary. Okay, that part's not completely necessary, but I don't want to have to deal with little weird things that happen when we have like a fractal boundary or something like that. All right, it's not necessary. You know what? I'm just going to get rid of this. Sorry for that weird digression. Okay, let omega be an open, bounded domain. In my mind, I'm thinking about a blob, but you could have like a weird fractal boundary, I guess. So let omega be an open, bounded domain, and assume that two things: delta u is identically equal to 0. The equiv is going to give me 3 bars. Is identically equal to 0 in the interior of omega, which is just, I'm saying omega is open, so its interior is equal to omega, but I'm just going to be redundant there because I guess I would emphasize it. Let u be equal to, okay, and continuously and twice continuously differentiable. I'm sure I'm not spelling that correctly, and it will tell me how to spell it. And twice continuously differentiable on omega, and continuous on the closure, the omega and its closure. Okay. Let me make sure that's saying like I want it to. What's happening here? Why is that not showing up? Oh, because I'm not in the right thing. Okay. Wow, I missed that by a lot. Sorry, just trying to separate this so we can just have... Okay. All right, then the weak maximum principle says, then if you look at the maximum on omega and its closure, maximum of u is equal to the maximum, is equal to the maximum of u on the boundary. Okay. So the maximum of u over the whole domain, including the boundary, or I should say the maximum of u over the closure of omega is equal to the maximum of u over the boundary of omega. So what this says is that the maximum occurs. The maximum occurs on the boundary of omega. This principle alone does not say it doesn't occur in the interior of omega. It just says it does occur on the boundary of omega. Okay, so for this we're going to use the second partial derivative test, the second derivative test for multivariable. So this is what it is this is it. It's on Wikipedia, but it's also in your calculus book. So what we're going to look at, let's look at these. This is the second derivative test. Let's look at what the different things are. So our variables are x and y instead of, like this, our variables are x and y, but we have u instead of f. So d of ab. So what is that? It is going to be the second derivative, the second x derivative times the second y derivative minus the square of the mixed partial derivative. And if the second derivatives are continuous, fxy equals fyx, which is why if you look at the determinant here, it should be minus fyx times fxy. but fxy equals fyx if we know that the mixed partials are equal, so we have this formula here. So we're going to do this, but with u. So we're going to argue by contradiction. So this is where I'm going to give like a wrong answer, okay? And it's going to motivate where the perturbation comes from. So assume that x naught, y naught is in omega. And again, I'm going to write in the interior of omega, which it is omega. Omega's open, so it's equal to its own interior, but I want to emphasize that we're in the interior of omega. So assume that x naught, y naught is in the interior of omega. So assume that x naught, y naught is in the interior of omega. Okay, so what's going to happen now, and that there is a local maximum at x naught, y naught. So essentially what I'm trying to prove now would be the strong maximum principle, because I want to prove that this is not going to work, but essentially if it did work, what I would be showing now is that there is no local maximum. So if this did work, I would be showing the strong maximum principle, which there is no local max in the interior of omega. This isn't going to work, but again, I think by doing this, it will illustrate like the fix that the perturbation comes from, or it'll explain the fix of the perturbation. Okay, so all right, so we want to compute u xx of x naught, y naught times u. You know what? I'm going to use my standard notation, so it's going to be pxx of x naught, y naught, pyy u of x naught, y naught, and then minus, let's see, do I have that pxy command somewhere? No, I don't. Okay. I don't know, I don't have pyy either. So let me go ahead and add that. Okay, whoops. All right. Where are we? Nope, okay. Minus, minus pxy u of x naught, y naught squared. Okay, I want to see if this looks like I want it to look. It says there's a problem there. What did I have up there? Did I keep it as pxx or something? There we go. Okay. And then I made that same mistake that I've been making. Okay. All right. Okay. Now, since the Laplacian of u is 0, this means pxxu plus pyyu is equal to 0. And so what we get here is pxu equals minus pyyu. So the above is the following. So what we get from the above, if you look at this part right here, pxx is minus pyy. Actually, I want this to be a little different. I want to say pyy is equal to minus pxx. Same thing, doesn't matter, but I want to have it this way. So then the above is going to be minus, see, it's pxx times minus pxx. That's going to give me minus pxx u of x naught, y naught, squared, and then minus this squared. Oh, two minus signs there, which is going to be equal to minus this. I'm going to have to change that minus to a plus. Oops. Now, what we really want to say is, okay, we have a sum of squares, and we have a negative sign. So this is less than 0. That's what we want to say. We have a sum of squares with a negative sign. So it's got to be less than 0. Square is positive. Okay, maybe you're being like, wait, what? Square is positive, means greater than 0. Multiplied by a negative number, that gives us something negative. If we come over here and see what we have, if d of AB is less than 0, which is what we're saying, if d of AB is less than 0, then we have a saddle point. And so it's like, well, wait, we must be done here because this is positive. We take a negative, we get a negative. This says if that's less than 0, we have a saddle point. Okay, well, What's the problem here? This is not necessarily positive. It's merely non-negative. So what happens if this is equal to 0? Well, if this is equal to 0, both of these guys have to be equal to 0. The double x derivative and therefore the double y derivative and the xy derivative have to be equal to 0. Well, let's come over here and see what's going to happen. If d of AB is equal to 0, then it could be anything. It could be a saddle point, it could be a minimum, a maximum, saddle point. The test is inconclusive if this is equal to 0. So if it's equal to 0, it's the test is inconclusive and we can't do anything. Okay, so maybe you're like, okay, well the test is inconclusive, but we know a little bit more. We have a little more information than just this is equal to 0. Because like I said before, we know the double x derivative, the double y derivative, and the mixed partials are all equal to 0. Do we have any things like that? Okay, so a condition implicit in this statement is that if the double x derivative or double y derivative is equal to 0, okay, so that's good. That's the case we have. We know the double x and double y derivative is equal to 0. It must be the case that this is less than or equal to 0. Okay, and therefore only cases 3 or 4. But that just says we're either at a saddle point or at an inconclusive point. Okay, so in other words, we really want to say we're at a saddle point, but we only know it's inconclusive. Okay, so here's what's going to happen. We're going to introduce a new function called u epsilon. So define u sub epsilon of xy to be equal to u of xy plus epsilon times x squared plus y squared. Okay. Then let's just try to compute a few things. If you do the second derivative, what you're going to get, the second derivative of u epsilon, what you're going to get is the second derivative of u. And then if you do the second derivative here with respect to x, it's going to be, the first derivative is 2 epsilon x, and then just 2 epsilon, so it's going to be plus 2 epsilon, and the second derivative, the second y derivative is going to be the second y derivative of u, plus, again, 2 epsilon. Okay. Oh, and then pxy u epsilon. Okay, if we do this, okay, let's do the x derivative. If we do the x derivative, we're going to get, let's do the x derivative first. We're going to get the x derivative of u. I'm going to have to put a y derivative here, but let's just do the x derivative first and then the y derivative. If you do the x derivative, it's going to be the x derivative of u plus 2 epsilon x. But now I want to do the y derivative of that. So if you do the y derivative of that, you get pxy there, and then the y derivative of that is 0. Okay, so plugging this into the 2-variable second derivative test, which again, I'm not going to say what it is, but I'm not going to write what it is, but you can look it up in your calculus book or Wikipedia, whatever. Okay, so if this is true, plugging this in the second derivative test, we get the following. Actually, hold on. Is this what I want to do? Yes. Okay, so we're going to have pxx. So, wait, no. Let me back up a second. So, actually, yeah, okay. Plugging this into the, this gives the following. I don't know how this is going to fit. Let's just start this out. So we got pxx u epsilon times pyy u epsilon minus, I think this will fit okay, pxy u epsilon. But, I'm going to have to write the variables. Okay, so let's see how this goes. Okay, and this is equal to, okay, so pxx of u epsilon is going to be this. And then times uyy, or sorry, the second y derivative of u epsilon. We're going to have this right here. Here. Okay, and then minus the is going to be this, minus this. Okay, I'm going to come down a different line here. Okay, now notice what's going to happen. I'm going to write it. I'm not going to write it all out, but notice what's going to happen. We're going to have the double x derivative times 2 epsilon plus 2 epsilon times the double y derivative. That's going to be 0 because u is harmonic. So then what we're going to be left with is the double x derivative times the double y derivative and then plus 4 epsilon squared. So we're going to have pxxu of xy plus, actually, let's see, we're not going to have, yeah, you know what, okay, I don't need to have the variables here. Okay, it's going to look a little cleaner if we don't write the arguments. I don't like to write the arguments a lot for a number of reasons, but I think it just looks cleaner. It's one of the main reasons I don't like to do it. Okay, so now what we're going to get is we're going to get pxxu times pyyu and then plus 4 epsilon squared, and then, oh, sorry, there's a mistake here. There's a mistake here. That's a crucial mistake. Sorry, you guys are probably like, you forgot that. You forgot the square. Okay. And then, right, minus the xy derivative of u epsilon squared, but that's just the xy derivative of u epsilon, so we're going to have that. All right. But now we can write this last part as minus. So actually, let me stop here. Since pxxu plus pyyu equals 0. Do I have that right there? Yeah, this is what I want here. Yeah, okay. So now what are we going to have here? This is equal to minus, okay, it's going to be very similar. It's going to be basically, no, okay, let me just do this. It's going to be minus pxxu squared minus this guy squared plus 4 epsilon squared. I'll just do this. Okay, so it's going to be minus, and we're going to get, again, it'll be a sum of squares. Okay, plus 4 epsilon squared. Okay, let me make sure that's going to be what I want it to be. What happens here? Why doesn't it have the 4 epsilon? Does it go down on a new line? I don't understand this. Oh, because it's right here. Okay, good gosh, Rob. All right, we can get rid of that. Okay. Oh, got a problem. Here we go. Okay, so now we have this. Okay, so again, we're going to have two different things. Okay, if we evaluate this, okay, so now what we want to do is we want to evaluate this at a particular point. At a this is, I don't think I need to state this explicitly like as a proof by contradiction here. I don't think that's going to be what it is. I don't think that's logically going to be what it is. But it is helpful to talk about this at a particular point. Okay, there can be two things. There are two possibilities. First, if this inside part here is equal to 0, if that, sorry, let's say if that's not equal to 0. I don't need this. If this is not equal to 0, then so notice that this right here, importantly, the double x derivative of u at x naught y naught plus the xy derivative of u at x naught y naught, that does not depend on epsilon at all. So whatever the epsilon is, whatever u epsilon is, this part is going to be the same. So if this is not equal to 0, then for sufficiently small epsilon, for sufficiently small positive epsilon, like even if this number is like 0.000001, we have minus 0.000001, eventually 4 epsilon squared is going to be less than that in absolute value, and so this whole thing is going to be less than 0. Okay. So if that is not equal to 0, then for sufficiently small epsilon, this quantity here, this is less than 0. Okay. Since, I'm going to say, since that is less than 0. Strictly less than 0, not less than or equal to 0. Okay, in this case, by the second derivative test, u epsilon does not have a maximum at x naught y naught, because that thing, that d, this discriminant thing, is going to be less than 0. Okay, so there are two possibilities. First, if it's not equal to 0, we can just apply the argument that we wanted to u. If it is equal to 0, then it becomes the following. And this is where the epsilon comes into play. This is equal to just 4 epsilon squared. And this is greater than 0 because epsilon is greater than 0. Okay, so now what are we saying? We're saying that thing is greater than 0. We're saying that thing in the second derivative test is greater than 0. Well, let's come here. If this is less than 0, what does this say? It says if it's greater than 0 and the double x derivative is less than 0, then we're at a local minimum. That is what it says, but that's not the row. So let's look at items 1 and 2 here. Okay, d of ab is greater than 0. d of ab greater than 0. That's where we are. What does it say here? This is greater than 0. Now, part 2, if the second derivative is greater than 0, then we're at a minimum. If the second derivative is less than 0, we're at a maximum. Okay, now remember, this right here, the thing that we just computed, is the DAB, is the D thing, this, what is it, the determinant, so the thing that we just computed is the determinant, not for u, but for u epsilon. Okay, so now when we have this condition, fxx greater than 0, fxx less than 0, it's not u, the double x derivative of u that's greater than 0, or the double x derivative of u that's less than 0 that we have to care about. It's u epsilon. Okay, so note that pxx u epsilon, pxx u epsilon, the double x derivative of u epsilon, is equal to the pxx derivative, the double x derivative of u plus 2 epsilon. And if this is 0, and if this is equal to 0, if this is equal to 0, well, it's a sum of squares. And so if it's a sum of squares that's equal to 0, both terms have to be equal to 0. Then pxx u of x naught y naught, y naught is equal to 0. And so pxx u epsilon x naught y naught is equal to 2 epsilon, and that's greater than 0 because epsilon is a positive number. So by the second derivative test, x naught y naught is a local minimum for u epsilon. In particular, I'm being really vague, and my colleagues probably wouldn't like this. When I say x naught y naught is a local minimum, I mean there is a local minimum. Let me say this. Okay, let me say it rightly. U epsilon, has a local minimum at this point. Okay. In particular, there is not a local maximum at x naught, y naught. And this reminds me, I want to say a particular point x naught, y naught in the interior of omega. Okay, the conclusion is that u epsilon does not have a local maximum in the interior of omega. So the conclusion is that u epsilon does not have a local maximum in the interior of omega. Okay, well that's good. That tells us about u epsilon, but what we really care about is u. Well, so we know that u epsilon, u is continuous, so u epsilon is continuous. So we know that the maximum of u epsilon has to occur on the boundary. Okay, we know that u epsilon has a maximum in the closure of omega because it's a continuous function. So therefore, it has to be on the boundary since we just showed it's not in the interior. Okay, so what we're going to have now, so what we have now is that the maximum of u over omega is going to be less than or equal to. So notice that we're doing u epsilon is u plus epsilon times x squared plus y squared. So point-wise, u is less than u epsilon. So we're going to have this is less than or equal to u epsilon. Okay, good. Well, the maximum, again, if we look at the maximum of u epsilon over the closure of omega, well, it's either going to be in the interior of omega or the boundary of omega. And we just showed it's not on the interior of omega, so it must be on the boundary of omega. So this is equal to, let's see, yeah, the boundary of omega. Got a problem here. Okay. Okay. But now we're going to do this interesting fact here. This is less than or equal to, it's going to be less than or equal to the maximum. It's going to be less than or equal to the maximum of u on the boundary plus, and I want you to actually think about why this is true, plus epsilon times x squared plus y squared. I'm probably going to need to scroll down or to split this up, but I'm probably going to need to split this up. Okay. I'm probably going to need to split this up, but I can pull, okay, so why is this true? If you have the maximum of two functions, the maximum of the sum of two functions is less than or equal to the sum of the maximums, okay? Think about why that's true. But I'm going to have to bring this epsilon out here to get something like this. Let's see how that looks. What is the problem here? Partial. Oh, partial. Okay, so we're going to have this. Then we're going to have this. Then we're going to have this. Okay. All right. Oh, and these are all lowercase omegas. How many times have I done that, I wonder? Oh. Nope, not much. Okay. All right. Now, what this means, okay, so now what we have is this, the maximum of u over the closure is less than or equal to the maximum of u over the boundary, plus epsilon here. Oh, I need to get rid of this epsilon here. Now what's going to happen is the maximum of x squared plus y squared over the boundary of omega is less than, we know omega is bounded, so we know the maximum of x squared plus y squared is less than or equal to something. This is less than or equal to, I'm just going to write all of this, times m, where m equals the maximum, where m is equal to this right here. And we know it's finite, which is finite since omega is bounded. Okay, so now what do we get here? All right, so now epsilon times m, that goes to 0. Okay, so this is true for all epsilon greater than 0. So what this means, we've used this before, this is the thing that we care about, is less than, the thing that we care about is less than or equal to this plus epsilon. This can get as small as we want. So if this quantity is less than that quantity plus anything that can be made as small as we want, it means actually this is less than or equal to that. Okay, hold on a second. Okay, this is true for all epsilon greater than 0, so the conclusion that we make is this is less than or equal to this. So this says the maximum of u over omega of the closure of omega is less than or equal to the maximum of u over the boundary of omega. Now we know the other inequality. We know that the maximum of u over the boundary of omega has to be less than or equal to the maximum of u over the closure of omega, and this is just because the boundary of omega is part of omega, or part of the closure of omega. So the maximum of u over a smaller set is less than or equal to the maximum of u over a bigger set. So then we've shown that they're less than or equal. We've shown that both the inequalities, this is less than or equal to that, and that is less than or equal to that. So therefore, we get the conclusion that they're equal. Okay, so there's kind of a lot of logic going through here. Make sure you understand it all if you want to understand the proof of this theorem here. Okay, so that is it. That was a long video to make this solution. But this is the solution. You know, I kind of like this problem for a number of reasons. Maybe it drove you crazy.